So our last thing we want to do is to dualize our SVM problem. Well, why do we want to do that? So recall that for our SVM problem, either for imperfect or perfect or imperfect separation, we are always able to solve it because it's a convex program. Okay, but it does not mean we want to solve it directly. Recall that for linear programming, if you have a primal linear program, you always have a way to solve it. But sometimes we want to solve its dual program because sometimes it gets easier. So some researchers, they study the SVM problem and they find that, oh wow, the dual program is easier to be solved. So let's see what's that. Okay, so let's try to find the dual of the SVM problem. So we of course want to do Lagrange duality. Okay, so we're going to first take the Lagrangian. So let's say lambda I and mu I are Lagrange multipliers for constraints. Lambda I are for the constraints that is talking about the imperfect separation. Okay, previously your yi times whatever should be greater than or equal to 1 minus gamma I. So now you use the bigger side to minus the smaller side. That's how you get the term inside the big the square brackets. Okay, and the lambda I multiply this gap. Mu I multiplied by gamma I because you have a constraint saying that your gamma I is non-negative, right? So that's how you do this all the things and get your Lagrange multipliers here. So to recall you that this is a minimization problem, so what we want to do is to make sure that our lambda and mu should be non-negative, so that whenever you really have a feasible term here, your lambda is rewarding your feasibility. Okay, so that's Lagrangian. Once we have that, the Lagrange dual program is to choose lambda and mu in the right way to maximize the outcome of this minimization. And we know that minimization of Lagrangian always gives us a lower bound. So we choose lambda and mu to maximize the lower bound. That's Lagrange duality. So now let's take a look at the inner program. We want to choose alpha, beta, and gamma to minimize the whole thing here, alright? And here, alpha is just one scalar. Beta is a vector from beta 1, beta 2 up to beta n. And the gamma is, okay, again a vector, gamma 1, gamma 2 up to gamma m. So we need to do the first order condition because it's necessary and sufficient. It's the most powerful tool we have, right? So actually you may do all the derivations by yourself, but let me just try to give you some hints. So for alpha only exists here. So alpha, this function is actually linear to alpha. So once you do that, the only thing remains is this guy. That's why you get this. Okay, so that's for alpha. Regarding beta, beta has a nonlinear term here, also a term here. So once you do differentiation, your beta goes from here, and your beta has a coefficient here, lambda, y, and x. That's how you get things here. So I'm saying it very quickly, but you may want to help yourself by doing all the careful derivations. The last one is gamma. So for gamma, it exists here and here. So once you do the differentiation, you're going to see that also here. So your C comes from here, your lambda I comes from here, and your mu comes from here. Okay, so you know how to do the differentiation. An interesting thing here is that the first and the third set of constraints, they don't have primal variable. They don't have alpha, beta, or gamma, right? So what does that mean? Whenever you are doing an optimization to try to minimize the whole thing here, you must make sure that your dual variables are chosen appropriately to make this and that happen. Otherwise, you may adjust alpha or one of your gamma to make the whole problem here negative infinity. Alright? Otherwise, I say it in another way. If your dual variable does not satisfy this and that, then your Lagrangian minimization problem will be unbounded, just like what we did when we are saying that linear programming duality and the Lagrange duality is actually somewhat equivalent for linear programming. Okay, so I hope this does not seems too weird for you. And now we have two things to be satisfied by dual variables, and they will be able to be used to simplify our Lagrangian. So our Lagrangian can be simplified. Once we know this and that must be true, then you will be able to take out some parts. For the coefficient of alpha, they must be 0. That's how this term here disappear, and alpha also disappear. And also your C term and your lambda gamma term and your mu term should go away. Okay, so that's how at the end you get the simplification here. This and that, they are the same thing. All right, and then this particular term corresponds to only y, this guy, and your last, this minus 1 gets you this. That's pretty much how you do the simplification. And once you do that, the next thing to do is that your beta has been optimized. Your beta should be chosen in this way according to your x, y, and the lambda. So you may plug in this into beta. That's how you get this and that. So now again, you get a giant formulation with a lot of summation, superscripts, subscripts. After careful arithmetics, you're going to get this one. Well, I don't have time to here to do all the derivations for you because high school arithmetics. So please try it by yourself, but it's of course not a weird thing. Just do some arithmetics. Okay, so here you may see we have lambda multiplying each other, y multiplying each other, and x multiplying each other, some kind of symmetry. Okay,